The problem begins with 25 women between the ages of 70 and 80. So this is a z-test of a sample mean problem. For this problem, just solve it using those 5 steps that we've gone through so far. And I'll give you guys 5 or 6 minutes to do this problem. Then we'll go over it together. That's not coming from me or anything I'm doing. No? Oh, for those of you on Zoom, what I've shared on the screen, this is the problem I would like you to do right now. Problem 1. I'll give everyone another 2 minutes. All right, let's get started. All right, let's just bring this up. All right, so for this problem, what is the sample mean? Yes? That's correct. So the first thing you should do for all these problems is just write down all of the information you know. So in this case, hold on. The image is super zoomed in. So we know that our sample mean is 1.5 seconds. What else do we know about our sample besides the mean? Yes. So what is the sample size? Yep. There are 25 of these 70 to 80-year-old women. So we know these, but now let's talk about the null hypothesis, the alternative hypothesis, population 1, and population 2. So this is step 1 of the hypothesis testing procedure, so I'll just denote it as 1. So if we want to know what population 1 and population 2 are, can anyone tell me how they define population 1 and population 2? So for this particular study, they're comparing the general population of women between the ages of 70 and 80 to women in the same age group who went through a quote-unquote special program. So I would say, based on the convention of choosing population 1 as the population that represents the null hypothesis distribution, I would say population 1 is all women between 70 and 80 years old. So if that's our population 1, which is the null hypothesis we're comparing our sample against, how would we define population 2?
Women aged 70 to 80 who underwent a special program.
Yep. '70 to 80-year-old women who went through the special program. So the first step of the hypothesis testing procedure is not just stating our two populations, but also stating the null hypothesis and the alternative hypothesis. So the null hypothesis is H subscript 0. So what would be the null hypothesis in this case? You could state it in words or as a comparison of different group means. Let's do it in words first. So the null hypothesis should mention both of the populations that are also stated. So what would the null hypothesis state about these two populations? Yes. Perfect. Null means 0. So our null hypothesis, there is no difference in reaction time between population 1 and population 2. So now let's talk about our alternative hypothesis. based on how the question is framed, what should our alternative hypothesis be? I'll go back to the text of the problem briefly. So based on how the problem is framed in the question, what should our alternative hypothesis be? Jen?
Women who underwent a special program will decrease their reaction time.
Yep. Perfect. I'm going to amend that a little bit. So instead of saying the program decreased time, say that the mean reaction time for population 2 will be less than population 1. They're saying the same things, but stating it in terms of population means is going to be how we ultimately do the comparison. So we can state alternative hypothesis, population 2 will have lower mean reaction time than population 1. All right, so that is the core of step 1. So for step 2, what we're going to do is we're going to define the characteristics of our comparison distribution. So the comparison distribution is one of 2 distributions. There's the distribution of scores, also known as the population distribution, and then there's the distribution of means, which we also call the sampling distribution. And if you recall, I encouraged you to draw out the relationship between the distribution of scores and the distribution of means as 2 overlapping normal distributions, one above the other. Where at the top of the page is our distribution of scores. And below it, we have our distribution of means. And I'm going to be drawing the distribution of means as slightly skinnier with less variance than the distribution of scores. So based on other things we were told in the problem, what do we expect the mean of the distribution of scores to be? So the mean of the distribution of scores, aka the mean of the null hypothesis distribution, what do we expect that mean of this distribution to be? Its mean and its standard deviation. Jen. That's correct. And those were given to you in the problem. And those refer to this distribution. So the mean is just the center of the distribution. And I'm going to draw this dotted line going from the mean of our distribution of scores to the center, or the mean of our distribution of means. Do you remember what term we used to describe the characteristics of the sampling distribution? We didn't just use mu and sigma, we used something to indicate that they were from a different distribution. Anyone remember? You'll probably recognize it. We used the little subscripts m. So mu subscript m is the mean of this distribution of means, and we use subscript m to indicate the standard deviation of the distribution of means. Does anyone remember what the name we gave? There was a special name or term that we used for the standard deviation of this distribution of means? Yes. That's right. So standard error of the mean, also known as SEM. So based on what we know about the mean and the standard error and the standard distribution of our distribution of scores, what is the mean of our distribution of means? Yes. Sorry? 1 point what? So it wouldn't be 1.5. 1.5 is our sample mean. And this distribution here is what we would expect if the null hypothesis is true. The mean of the distribution of means will always equal the mean of the distribution of scores, not the sample mean. So this will actually be 1.8. And I can actually write this out. So the mean always equals the mean of the sampling distribution. This was something we called in the textbook Rule 1, because it's one of 3 rules of inferring the characteristics of the distribution of means from the distribution of scores. So we now have our mean of our sampling distribution, 1.8 as well, but now we need to calculate the standard error of the mean. So to do this, we need to know the formula for the standard error of the mean. I bungled this last time. I forgot the square root symbol, but please don't do that yourself. So this equals the square root of the variance divided by the sample size of your sample. So to find the standard error of the mean, we take 0.5 and we square it. And then we divide by the sample size that our mean had, 25. So if I did this correctly, so if I'm not mistaken, this is 0.1. Did other people get that as well? All right, good. So now that we know this is 0.1, we can do a little bit of a sanity check just to make sure that we're getting results that we expect or are reasonable. Notice that the standard error, the standard deviation of our distribution of scores is 0.5, and for our standard error of the mean, it's 0.1. Will the standard error of the mean always be lower than the standard deviation? I'm getting some nods. Yes, the standard error of the mean will always be lower. And that's because in order to get it, you have to take the square root as well as dividing by a number greater than 1. So we now have all the information we need to move on to the problem and actually compare the sample mean to our comparison distribution. So for this kind of problem, our distribution of means is going to be the comparison distribution, which is to say it's going to be the distribution that we find the sample mean on and then see whether that sample mean falls within a certain critical region, falls outside of a critical region. But before that, we need to talk about where our sample mean falls. Well, actually, let's actually, sorry, I'm getting ahead of myself. So step 3 is going to involve looking up what the z-scores we should use to either reject or fail to reject a sample mean. In the problem, we were given clues about the kind of tailed test and the alpha level or significance level of this problem. Can anyone tell me what those were? So according to the problem, we were told to do the hypothesis test at the 0.01 significance level. And based on the way the problem was phrased, where it states in the problem that you expect this course these women take to decrease their reaction time, that means we expect to be doing a one-tailed test. And what kind of one-tailed test? One-tailed upper or one-tailed lower? When you expect the mean to be lower than the null hypothesis predicts, what kind of tail test should that be? Yes. Yes. So those are the two factors we need to figure out the z-scores that will be our critical z's. Always forget I'm not in MS Paint. There we go. So we learned before that the alpha value for this problem will be 0.01, and we will be doing a one-tailed lower test. So if we're doing a one-tailed lower test, that means we're going to be looking at a single z-score that marks the lower 1%. So we have the lower 1% of the distribution on one side, and on the other side, we have the upper 99%. And the question is, given the characteristics of this distribution, does our sample mean fall here, which is to say outside this region of rejection, or does it fall here or here, inside the region of rejection? So how do we find that out? Well, we'll need to find the z-score that corresponds, well, let's find the z-score that corresponds to our sample mean. So the z-score of a sample mean is given by our sample mean minus the mean of the distribution of scores, the null hypothesis distribution, divided by the standard error of the mean. So this was 1.5 minus 1.8 divided by 0.1. So that gives us minus 0.3 divided by 0.1. Make sure I don't make a mistake. I'm using Excel to calculate this. So this gives us a z-score of minus 3. Did everyone get that as well? All right. So we now have the z-score of our sample mean, which is minus 3. But how does that compare to the critical z that'll sort of form the boundary between the region of rejection to everything on the lower tail and the failure to reject region, which is everything else? So what we need to do is realize that all the information for finding that critical z, I'll call it z lower to indicate that it's the lower critical value. It looks like z lower, but that's not correct. You could go to the, you could go to the Shiny app, which is what I'm going to do. So the Shiny app is your friend. If we choose a one-tailed lower test, and we choose as our tail probability, which is our critical value, or alpha value rather, 0.01, it gives us that the z-score is minus 2.33. So if our critical z is minus 2.33, how does that compare to the z-score of our sample mean, which was minus 3? Will it be in the region of rejection or outside the region of rejection? Were you raising your hand? So if we have a z of minus 2.33 as this one I'm indicating here, and everything below this would cause you to reject, oh, go ahead. Okay, sorry, I didn't see your hand raised. So everything below minus 2.33 would cause you to reject the null hypothesis. And since our critical z, our z value of the sample mean is lower than that, we would reject the null hypothesis. Were you about to say that? Oh yeah, of course. So the comparison we just did, you can either just eyeball the numbers and see that the z-score of the sample mean is lower than the critical z-score, or you can actually draw the diagram like we see here, and you can find the sample mean on the diagram and just see that it is in this region of rejection. Either way, at the very end of the problem, state your conclusion in terms of rejecting or failing to reject the null hypothesis. And in our case, should we reject or fail to reject our null hypothesis? Well, I believe that we should reject the null hypothesis because if our sample mean is more extreme than our critical value, that is cause for us to reject the sample mean. That is cause for us to reject the null hypothesis. I'll mute Discord in just a second. Sorry, guys. So be sure to state your conclusion in terms of the null hypothesis being rejected or failing to be rejected. And before I let you guys off and do a problem on your own, I want to quickly just go back to the beginning of the problem at part 1, where here we stated the alternate hypothesis and null hypothesis in terms of words, but a totally legitimate alternative way of doing this, hold on, I'm just going to mute Discord now, sorry guys. Well, a legitimate way of doing this would be for you to simply state the population 1 and population 2 as means labeled mu1 and mu2, and state which one you expect to be above the other. And I'll show you in just a sec as soon as I turn off Discord, which is being a pest. All right, there we go. So let's say that we were looking at two potential distributions, which will come up later when we talk about power, but here just hypothetically. Imagine we had population 1 and we called its mean mu1, and for population 2 we did mu subscript 2. We could state the null hypothesis as mu1 equals mu2, because if the two populations are the same and the program had no effect, you'd expect no difference between the group means. For alternative hypothesis, we can state it in one of two different ways. We can state it as mu2 will be lower than mu1, or we can say mu1 will be greater than mu2. Does that make sense? Did I make a mistake there? No, okay, that's correct. So that's a totally optional way of presenting it. If on your exam you define population 1 and population 2 in one way with words, and you use mu1 equals mu2, and then you just use mu1 and mu2 here to show the relationship being either higher or lower, or either higher or lower for a two-tailed test, I'll give you full credit on that. You don't need to put it into words if you have defined population 1 and population 2 correctly. So if you go to the in-class assignment for chapter 5, because it's divided across two different pages, I want you to do the first couple problems, and I want you to stop after you finish the word problem that's similar to the one we just did. So, oh, I'm sorry, do all the problems on this, my bad. I'll give you guys 15 minutes to do these problems. There is a page 1 and a page 2, so make sure you're doing both sides. For people who are over Zoom, these are available on Blackboard. They're at the top of the lectures page. Just download them. And if you have some paper, be sure just to like write them out, take a photo of the results and try to paste them into the Word file so that I can see you've done the work. Yes. I'm sorry? These ones, I'll be posting the answer key after class, but no, not right away. Yes. Oh, yes. Don't do the chapter 6 one yet. There'll be a second half of the class. You're welcome to get started with it if you finish earlier. You have another 5 minutes and then we'll continue. All right, 1 more minute. All right, time's up. Let's move on to the material from chapter 6. Well, actually, scratch that. Let's move on to the second part of, oh my goodness. This problem had a confidence interval calculation at the end. So let me actually go over a confidence interval calculation based on the problem we just did. Apologies for not getting to that. Yes, the problem you just did had a confidence interval calculation. Sorry, I mentally misremembered confidence intervals appearing in chapter 6. Sorry. So for the problem we just did, let's compute the confidence interval. And let's say that we're sticking with that original alpha value of 0.01. But there's something about the confidence interval calculation that's kind of unique, which is that the confidence interval calculation cannot be done with a one-tailed test. So a one-tailed test is simply inappropriate for the confidence interval calculation. It assumes a two-tailed kind of analysis. So I'll just put that in brackets, two-tailed. So for the confidence interval calculation, it is actually equivalent to the calculation we just did and the problem we just did of a z-test of a sample mean. So we had for this problem a mean of 1.5, and we had a standard deviation, we had a sample size rather, of 25. We also had a standard error of the mean that we went to the trouble of computing at 0.01, at 0.1 rather. And for the confidence interval calculation, I give on the worksheet that I post online but did not print out for you guys a very, very helpful set of tools for how to solve confidence interval problems. So when you're doing practice problems, I recommend that you look to the confidence interval problems and how to solve. Hold on. There they are. So I have a whole page, confidence interval calculations, facts you need to know. You need to know the sample mean, the standard error of the mean, and whether it's a 95% or 99% confidence interval problem. This is on page 3, I believe. Sorry, on page 4 of the worksheet that I gave you online. Apologies for not printing it out. That was just a careless error. So the 99% confidence interval, that is equivalent to a two-tailed test at the alpha of 0.01 level. So to go back to the problem, for a two-tailed test at the 0.05 level, at the 0.01 level, we're going to have two critical z's. We're going to have a lower z of minus 2.58. It's minus 2.58 because that's 0.01 alpha level, two-tailed test. And the upper z will be the same value, just positive. So for this particular problem, well, for the problem that I gave you, I'm not going to grade the confidence interval part because I didn't give you enough context. I didn't do a previous example. Sorry about that. But remember that for the confidence interval problems, there really is no equivalent to a comparison distribution. But if you think about the distribution that you'll be working with for the confidence interval problems, it is a sampling distribution in the sense that it is a distribution of means. So it is a distribution of means, just like the distribution of means for the z-test. However, the difference, can anyone tell me the difference between the sampling distribution for a confidence interval calculation as opposed to a z-test of a sample mean? There's one difference. One of the parameters changes. So what changes is that whereas before, for the previous kind of problem, we always said that the population mean equals this sampling distribution of the means. This time, that's not going to be true. Instead, our distribution of the means, the mean of this distribution, will be equal to our sample mean. So, yes?
Is it always going to be a two-tailed, even if the problem is looking at a one-tailed?
Yes, this is a good question. A student asked me that last semester, and I looked into this. It is not commensurate. You literally cannot do the equivalent of a confidence interval calculation because the confidence interval is looking at a range above and below just by design. This is mentioned briefly in the textbook, but when it asks you in the problem, it assumes that for the 0.01 level, do a 99% confidence interval. But that's a very good question. If you're asked, there's no such thing as a one-tailed lower test, and then the confidence interval of the sample mean for that one-tailed lower assumption. It is always with an assumption of a two-tailed test. This is another reason why one-tailed tests are really bad, because they are not compatible with the confidence interval. All right, so we have, once again, the distribution of means. But that's a very good question. Thank you for asking. So here, the center or the mean of this distribution of means is going to be 25, or sorry, 1.5 rather. We're going to call this mu m, mu subscript m, because it is the mean of a distribution of means, just a different distribution of means that's centered on the sample mean rather than the mean of the population of the null hypothesis. So what we have here is the mean of this distribution, and we also know its standard error of the mean. So the standard error of the mean is actually going to be the same as what we calculated for the other problem. However, the only difference is that instead of being centered on the population, the null hypothesis distribution mean of 1.8, it's on the sample mean of 1.5. So now the question is, what is our lower confidence limit and our upper confidence limit? Because remember, our confidence interval is always going to be expressed like this. Confidence interval, CI, then in parentheses, in this case because it's a 99% confidence interval problem, and we know that because it's a 0.01 significance threshold. It's always going to be a range of values starting from the lower confidence limit all the way to the upper confidence limit. So how do we find the confidence limit, lower and upper? Well, the answer is we're going to be relying on the fact that we know the z-scores that correspond to this Markov. So this should look similar to the two-tailed test where we have an upper and a lower z-score. So to find our lower confidence limit, it's going to be our mean plus the lower z-score times the standard error of the mean. And the confidence limit, the upper value, is actually going to be exactly the same, except the z-score in question is going to be the upper z-score. So what we're going to have for our lower z-score is 1.5 plus minus 2.58 times 0.1 And down here, for the upper confidence limit, it's going to be the same, except the z-score will be positive 2.58, but everything else will be the same. Also, last semester, someone pointed out that I draw the asterisks for the multiplication, like the eyes are drawn in the TV show Rick and Morty. I thought that was funny. And now that someone pointed that out, I can't unsee it. So let me just quickly go to Excel to make sure that I've done the calculations correctly. 1.5 plus. So according to my calculations, this upper value is 1.76 seconds. And this lower value is going to be 1.24. So for a problem like this, the way that you would express your answer is confidence interval, the 99% confidence interval, equals 1.24 to 1.76. And I go through this in more detail in the worksheet, which I wish I had printed out now, what the interpretation of the confidence interval calculation is, how to state it. So if you wanted to put this into words, let me just make this big. In our case, the 99% confidence interval is the range of values you are 99% confident includes the true population mean. So you don't know when you do an experiment what the population mean is. In the z-test of a sample mean, we assumed what the null hypothesis distribution's mean would be. But often in reality, we don't know that. And not only do we not know it, we don't even want to speculate. Because to assign it a value is to kind of be more confident than we actually are. So instead of saying confidently it is one value, you can simply say we are X% confident given our sample mean and our assumption about the standard error of the mean for this distribution. This is the range of possible values that would include the true population mean. And down here I have a question that I think really kind of like encapsulates the difference between the z-test of a sample mean and this confidence interval idea, which is just the comparison. I recommend you look at this and try to understand it. And the interpretation of a problem with a confidence interval calculation, assuming it's always a two-tailed test, so we can't necessarily do it here, but if you do a two-tailed test for an alpha value of 0.01, if you do the confidence interval of that sample mean with that standard error of the mean, and you find that the sample mean falls outside of the range of the confidence interval, that is always equivalent to saying that if you did a z-test of the same sample mean against a null hypothesis with a certain mean of its own, you would reject the null hypothesis. So finding your sample mean outside the confidence interval is unexpected and surprising in the same way that rejecting the sample mean in a null hypothesis test would be. So the back half of this is a lot less intensive on actually doing problems and more about concepts, so we can get through it more quickly. So for us to get started, I recommend that you open up the Shiny app about statistical power. This one. So for all your assignments, I completely recommend that you have this out at all times. It is a much more powerful tool than those power tables that are given in your textbook. And just like the standard normal distribution Shiny app, it would be cruel for me to expect you to do stuff by hand when I don't do it myself. And I think this is a better learning tool regardless. But it's important that you understand this tool, that you know how to toggle all the differences, and importantly, there are factors that affect statistical power that are actually not included as toggleable, if that's a word, options on this list. So the two options that are not included as modifiable variables on this Shiny app are sample size and effect size. Once again, I'm hitting myself over not printing out the full worksheet, but if you go to Blackboard and look at the worksheet, I have a similar kind of how-to guide for the power analysis problems. And last time we went into some detail about how changing certain variables in the power calculation, like changing the sample size, changing the standard error of the mean, changing the predicted effect size, changing what kind of tail test you're doing, changing the alpha value for the experiment you're running. We talked about how varying all of those affects statistical power. And we also talked about which one of those things is the most kind of linked to power. Spoilers, it was sample size. Sample size is majorly linked to, power is determined by mainly sample size and effect size, as well as, and everything else is kind of less significance, because you have the most control over the sample size of your study. You could always just enroll more people. And effect size, you have control over it in the sense that you can predict in advance a small, medium, or large effect size. So another aspect of this power analysis Shiny app is that it does not tell you power directly, even though I will ask you for it, but it does tell you the value of beta. And if you know that power equals 1 minus beta, if you know beta, you always know how to calculate the power. So beta is always given at the top of those plots on the right side of the page. So up here where my cursor is. So if you see for this preset, these presets, that beta is about 0.75. If beta is 0.75, what is the statistical power of this study? Jen? Yeah, it's about 26%, but if you round this up to 75%, it would be 25%. Yes, so the relationship between beta and power is very easy. And if I tell you for a one-tailed test with 0.05 significance level with a null hypothesis distribution centered on 100, alternative hypothesis on 105, with a standard error of the mean of 5, what is the power? You should be able to do that single step of looking at beta and doing 1 minus beta and figuring out what power is based on that. All right. So I mentioned that the two factors that influence power that are not represented on this Shiny app, they're not directly represented as things you can alter by like changing a number or switching a toggle, but they are represented in terms of the values that you input into some of these option menus affects effect size and is affected by sample size. So can anyone tell me which of these options changes effect size or corresponds to a larger or smaller effect size? Hint, effect size is roughly equivalent to how much overlap there is between the two distributions. Jen? Yep, changing the standard error of the mean would be a way of changing the effect size. So let's see what happens when we change standard error of the mean from 5 to 2. So suddenly there is a lot less overlap. But there's actually other things that we can change to affect effect size as well. So if you remember the formula for effect size, it had a numerator and a denominator. The denominator was the standard error of the mean, or it was actually the standard deviation, sorry. But there's other things that affect, sorry, I got confused. Let me just actually draw this out. The other two things that are affected, I don't know why I'm making this such a mystery, are the numbers you choose for the null hypothesis distribution mean and the alternate hypothesis distribution mean. So these would be, if you change these so that they're farther apart, it's a larger effect size, because effect size is d, and effect size d equals the difference between your two means for your alternate and null hypothesis, as well as the standard error of the mean, which you divide that difference by. And that's just about all I have to say about the power calculations, which we went over quite a bit last time. So I want you to take the remaining time to finish the second worksheet for chapter 6. Do as much as you can. Don't worry if you don't get to all of it. Yes, please. And I'll be posting the answer key as well after class. So something I'll send an email about later is I'll give a little bit of a demo of how to solve question 5, which is I think on the reverse side of the page. And this is something where using the Shiny app is pretty much a necessity. But the Shiny app makes this problem that looks like it's going to be really hard to solve actually incredibly easy, because it's just a matter of changing dials on that Shiny app tool. Yes, you can skip number 5. Please do questions 1, 2, 3, and 4. But I encourage you to do problem 5 on your own after I give you a video tutorial. Got to make a note to do that. Yeah, so I will do that. Thank you for reminding me. The thing is that the quiz 2 that I gave last semester didn't have confidence intervals on it. And it also went into, I believe, chapter 7 as well. So I'll post that, but it's not going to be as relevant as these problems that I gave you here. Thank you for reminding me. whenever you're finished, you're welcome to head out. Please leave your two in-class assignments in separate piles as you leave. Oh yeah, let me make a note to put that up there. Can you send me an email? I'll just send you the my spreadsheet. Just as you leave, put them at the top desk. Yeah, I don't think I ever specified that, just people started doing it. All right, so I posted the practice quiz too, though it'll be of limited relevance because of the material. But if you want to see the kind of multiple choice questions I might ask, some might appear. Oh, yes. Could you send me an email right now and I will just send them to you right now? Yes. So, sorry, what's your last name? Oh, okay, yes, you will get them right now. Yes, you're doing great. You don't need to worry.
Okay. Good to know.
There aren't many students, I can tell you that. Yeah. I just haven't posted them on Blackboard yet.
Well, that's kind of all I needed. If you want me to send me numbers,
I will. Oh, yes. Last name?
Hannah.
All right. Bye. Bye.